Hello, everybody. Thank you for joining us for this presentation. I hope you'll find it informative and not a cure for insomnia. And without further ado, here goes. So, as John's already mentioned, simulating devices in real-world SIL and simulator training applications is the topic. So simulators are a fairly simple concept. I think everybody, most everybody should know what this device is. But there are more than just flight trainers out there. First of all, there's trainers for operating trucks and boats, and also in the training realm, there's a great many devices that are designed as maintenance trainers. You wouldn't want the technician on a Seawolf submarine at 1,000 feet having to open up the control panel for the first time and repair something. He gets trained on a simulator somewhere above sea level. So you know what a simulator is. Maybe not everyone is familiar with the term SIL, but Systems Integration Lab. And the idea of a systems integration lab is to allow you to test the system functionality on the bench or in a safe location rather than having to try things in the air. In a real aircraft, you don't want to try a failure for the first time and see that it turns out to be catastrophic. In systems integration labs, there's a few different ways you can attack the beast. They can be totally simulated, where everything is a simulated, or it can be a hybrid, where some signals are simulated and some are from actual LRUs used in the aircraft, or it could be ship or other vehicle. And then even there's one step further you can go, and that we've also worked with SILs that there are both. There's simulated signals and the actual LRUs in a series of relays that can determine which one is online at any given time. And these are used to test new functionality of new LRUs or also to regression test any changes that are made in an LRU or a flight computer software just to make sure the new revision doesn't break something. So one quick thing to talk about is kind of the differences and similarities between simulators and SILs. Clearly, they're different functions, training versus system test, and but they're also surprisingly similar requirements. You need to function over the complete test system operating spectrum. It needs to be if the RTD runs in your application from -100C to +300C, the SIL function or simulator needs to also run for the full distance. They're often quite big with lots of I/O points. They often require fairly high fidelity and resolution. Plus or minus 10 degrees C is not a real expected signal in either an actual system or a simulator. One thing that they're almost always real time. In test systems, faster is pretty much always better, but in simulators and SILs, faster or slower is pretty much just plain wrong. You need to run them at the actual speed that the actual aircraft or other vehicle you're simulating is going to go. There's often a wide variety of signal types, and these are often large, expensive systems. So it's something you'll want to consider, end-of-life problems with, because these have long product lives. I mean, there's many simulators we work with that are 25 and 30 years old and are on their second generation of I/O. One quick thing to do. I don't know if there's people in the area or on the call that aren't from North America. In Europe, they don't seem to use Systems Integration Lab. They seem to use virtual/hybrid test bench. So just if there's any international folks here, maybe that'll help explain things a little bit. So moving on. So why would you want to simulate either in a simulator or a SIL? And the first and probably biggest reason is you can save money. Rather than training someone in a 747 that burns 3,500 gallons an hour and costs $25,000 an hour to fly, you can put them in a in a simulator that that costs, it may cost a few $1 million, but it costs very little out of pocket to keep going. In the SIL arena, you can simulate and save money because you don't have to use costly LRUs. The LRUs in the real aircraft are certified to DO 160, 178, 254, or sometimes mil-spec 810, 461, and these are very expensive devices. The simulated device doesn't have to be anywhere near as expensive. So another reason to use simulators and SILs is and more SILs probably than simulators, but it saves time. Time to market is key. Most of the people on this call are probably engineers, and your boss would always be happier if you got something done sooner rather than later. Other ways it saves time is it allows you to develop system development before the LRU is even available. You can find out how a proposed LRU works in a system before it's even developed, and probably fine-tune the LRU's capability before you actually have to finalize even the design in some test. And also it allows the LRU functionality to be tested prior. It says development on the slide, but certainly prior to installing into the aircraft. So, final reason to simulate, or final reasons, it increases development accuracy. The big thing, a lot of times, both simulator and SIL, what you're trying to event is the major oops event. You don't want to find out what happens when a sensor fails and you're at 40,000 feet for the first time. I mean, oops is, as I say, never a good thing to hear. Probably the only place worse to hear oops than a jet cockpit is in the operating room, and we won't go there. Other reasons to simulate development accuracy, it simplifies testing outside normal operating envelopes. You never want to simulate an engine failure on takeoff in a real aircraft. It's dangerous. You don't want to simulate the failure of an autopilot on approach in a real aircraft, but you can do it on the SIL and see what happens and make sure everything continues to function as expected. And I mentioned briefly before, it also simplifies ongoing testing of future revisions. When you change the software in your LRU or flight computer, you don't want to immediately just put it in the aircraft. You want to put it into a system and make sure it's still functioning and does everything it's supposed to. So I want to chat a little bit about simulation versus test, because they certainly come from the same worlds. And if I had to think of one word to describe the difference between simulation and test systems, the word would be continuous. When I think of testing an A to D system or a temperature measurement system can often be done in a couple of points. Even calibrating an RTD input system you can do in 2 or 3 points. Simulation needs to provide the complete range of the input, and also with reasonable fidelity. You can't test a control algorithm for a heat control system very effectively if you only have the ability to simulate 0 degrees and 100 degrees. You need much more resolution than that. So commonly simulated devices, and today we'll talk about the ones on the left here: thermocouples, RTDs, strain gauges, synchros and resolvers, RVDTs, LVDTs, a couple of general waveforms including phase and amplitude sweeps, 4 to 20 milliamps, and last but probably not least, just plain vanilla voltage. There's enormous numbers of signals in both training devices and SILs that are simply voltage inputs and outputs. And then part 2, which we haven't scheduled yet, but we're planning to work on, we'll kind of take this presentation into the avionics and comm devices part of the world. We'll cover ARINC 429, 708, 453, AFDX, the ubiquitous mil standard 1553, CAN, and some other serial devices. So the first specific thing we're going to chat about is thermocouples. And I'm not sure if everyone's familiar with a thermocouple, but basically, if you take 2 dissimilar metals and attach them, they create an output voltage called the Seebeck voltage. And that output voltage is not a linear function, but it's a well-defined function of temperature. So if you measure the input if you measure the output voltage of the thermocouple, you can convert that to temperature. And thermocouples are made of a variety of different items. I think constant tin, which is a copper nickel alloy, is pretty common, and that often gets mixed with either a second wire made of copper or iron. But most of you are probably familiar with the J, K, T, E, possibly R thermocouples. The primary challenge with thermocouples, and it's both on input, but in particularly while you're trying to simulate them, is they have a very small output. A typical, K-type thermocouple only puts out about 40 microvolts per degree C. It's hard to measure that. You can't do that with a standard D-to-A board. A standard D-to-A board, if you consider it's plus or minus 10 volts and 16 bits, that outputs 300. That makes it 305 microvolts per bit, which is about 7.6 degrees C on a K-type thermocouple, and that's not enough resolution to do a good job in a SIL or a SIM. The second challenge in thermocouples is the cold junction error. When you create a thermocouple, there's the two wires at the place you want to measure it, but then those two wires need to get connected to your system. And at that connection, you create another spurious one you don't want thermocouple, where the thermocouple wire attaches to your system. It's usually the system's usually copper, and the easiest way to get rid of that is in software, and you can measure the temperature at that cold junction, and you can compensate for it. But a reason you can't use a standard D-to-A board is because most standard D-to-A boards don't have that capability of measuring the cold junction. So I think thermocouples are probably more common in SILs and maintenance trainers than in flight devices, but many sims do use real LRUs, so they may require thermocouple simulators, for things like what's the exhaust gas temperature, what's the brake temperature, things like that. So one of the things I like to chat about in thermocouples is we run into people all the time that at least we feel have possibly unrealistic expectations of what you can get from a thermocouple. Achieving accuracy better than plus or minus about 1 degree C is very difficult unless you're using very, very special thermocouples and very, very special measurement equipment. And you have to remember also that the system's only as good as the CJC. If your CJC measurement has a 1 degree C error, your total system is going to be off by 1 degree. I think a lot of people overestimate how much 1 degree C is. I mean, 1 degree C is something you can easily change a board by. If you walk by a bench with the air conditioning on, it's easy to create a 1 degree C error. So again, just 1 degree C is a fairly tough thing to do with a thermocouple. Another thing you want to probably be aware of is thermocouples are not especially fast devices. Most simulators will run at a kilohertz, but you don't need to specify your thermocouple to run at a kilohertz, or many thermocouples. Excuse me, I'm getting tongue-tied here. You don't need to specify your simulator to run at 1 kilohertz. If the time constant on your thermocouple is 500 milliseconds, usually 10 or 20 hertz is about as fast as you need to sample them, because it kind of goes along with the settling time of the thermocouple. Other things that you'll want to include, especially in a SIL, is an open circuit setting on the thermocouple simulator board, because thermocouples do open now and then, and it's important for your flight control system to be able to know when that happened and know how to behave accordingly, not assume that things have gotten too hot or too cold. And be a little careful with grounding. If your system is using isolated grounds, you should certainly consider using an isolated output board. And even to reduce noise, we'd always recommend, if you can, use an isolated thermocouple simulator board. So I apologize for the shameless plug. I promise this is one of a few, but anyway, as you might expect, UEI does have a thermocouple simulator board. So it's called the DNX series, and the X can be A, R, or F, but I won't go into that detail here. But it's kind of, you know, modeled on the things we've already talked about. It's got, you know, sub 4 microvolt resolution, so, you know, less than 1/10 of a degree C. Built-in cold junction, isolated outputs. It'll emulate open and short circuit simulation, although short circuit simulation is not that big a deal on a thermocouple because they're pretty low impedance anyway. It does have readback, so you can read back the output voltage and current. It will go to 100 to up to 1 kilohertz, but you know, again, you seldom need to go that fast. And it does have a 10-year availability guarantee. And just as an FYI, I mean, this board was originally built for a large customer in a SIL application, and they so, you know, again, it was something specific for a SIL. The next thing we want to talk about is resistance temperature detectors. And I always thought it was called resistance temperature device, but I did some homework before I did this presentation, and it turns out I guess the official name is detector. But anyway, they're mostly made of platinum. They mostly have a gain factor, I guess you can call it a gain factor. It's called alpha in the lingo, of about 0.00385, and that turns out to be ohms per ohm. So in a 1,000 ohm RTD, you're running at about 3.85 ohms per degree C. Now the first thing we're talking about here is if you want to just build a test system, you can do it with three relays and 3 precision resistors. It makes a usable test. You can test at 3 different temperatures, and it typically works fine. But if you want to do a simulator, again, as we talked earlier, between the word continuous and kind of having the high fidelity to simulate all kinds of different devices or all kinds of different values of temperature, there's really 2 ways to do it. You can use a voltage output device, and that kind of fools your input device into thinking there's an RTD there, or you can use an actual variable resistor. The voltage output devices are nice. They can provide excellent resolution. The biggest problem with the voltage output devices is that often the LRU you're using has a self-test excitation current test, and the voltage excitation doesn't pass that. It really expects there to be a resistor there, and if you try and fool it with the voltage, it doesn't work. So you have to be a little careful. The next kind is a variable resistance. It's a programmable potentiometer device, programmable pot. It can also provide excellent resolution. Our experience is that programmable pots tend to be very temperature sensitive, and so for this type of thing, we have decided probably not, well, we decided in our design not to use them. And we went with Plan C here, which is a switched relay network device. It's basically a bunch of very high precision resistors with that get switched in with low resistance relays. It has very stable outputs. You can basically, depending on how many switches and resistors you want to put in, you can make the resolution arbitrarily large. And some devices using mechanical relays may have a life issue, but these days there's such good FET-based relays out there that you know, you can get that have less than 1/4 of an ohm on resistance that you know, will probably last, you know, forever. So so a little RTD notes. One thing you may want to consider before you even design your RTD system is whether there is a simulator available for it. There's not a lot of RTD simulators out there. You know, we don't make the only one, but they're kind of few and far between. So if before you kind of design around an oddball RTD, you know, a nickel or a copper or even a platinum that's an oddball resistance, make sure you can find a way to simulate it if you need to use a SIL or build it into a simulator. The larger the resistance, the greater the scale factor. So we find a lot of our cryogenic users go for the 1,000 ohm platinum RTDs, because down cold they can get very, very high accuracy. We find that a lot in the space industry. They use a lot of 1,000-ohm platinum RTDs because they've got a liquid oxygen and other liquid gases that are quite cold. Some RTDs are pretty fragile. You have to be a little bit careful. And for that reason, your simulator should be able to simulate an open circuit. Again, your system should be able to recover or at least warn that you have a broken RTD, and you need to be able to simulate that. And again, wiring can and does go wrong, so simulator should probably also be able to simulate a short circuit. In the SIL world, more than the SIM world, we find customers spending an inordinate amount of time trying to debug systems where wires are broken. As I mentioned, these things, once designed, are around for a long time, and it can take sometimes a day to find a broken wire. Whereas if you design just some fairly simple diagnostics into these boards, it becomes very easy to figure out what wire broke or what wire shorted. So, and again, so that leads us to, a good simulator or SIL can't have too much diagnostics. They work fine forever, but they're very complicated machines, and when something does break, it can take a long time to find out what happened unless you've built in the diagnostics. And similar to the thermocouple, and probably even to a more extent, don't expect your RTD to go very fast. An RTD with a rise time in air of less than a second is a pretty fast RTD. So I won't spend much time on it, but we do have obviously an RTD simulator board. This was again built for a very good customer who needed it for a SIL, although I have seen applications for it in simulator applications too. So then the next is a strain gauge. Like the RTD, a strain tester can be very simple. You only need a couple of resistors, but a strain gauge simulator is a more complex device. The strain gauge challenge is, unlike the RTD, has very small resistance changes, often only a few ohms full scale. So for like a 350 ohm strain gauge, sometimes 7 ohms will be full scale. It makes it pretty challenging to measure. And then there's a couple of ways you can do it. You can do a voltage out or a switched resistor. Voltage out is very tough in this case due to the very low output voltages that are typically provided. So a few notes on strain gauges, and in particular strain gauge simulators. Watch the resolution. There's a fair number of switched resistor out there. Make sure you're getting the resolution you need. Other things to watch out for is the excitation voltage limits. You need to make sure it's compatible with your system. There are AC strain gauges, and if so, make sure that your system can provide the bandwidth required. Again, check the simulator's full scale or the SIL's full scale output range, and make sure your strain gauge simulator can support it. Almost all strain gauges are measured in bridge configuration, so make sure that you're either purchasing a simulator that has the bridge completion resistors, or that you're prepared to add them yourself. And also check the wiring options, because there's 2, 4, and 6 wire connections. I won't go into details, but obviously we do have a strain gauge simulator board too. So our strain gauge simulator board actually is here. We designed that for a training simulator, and it was actually for the LIDS docking simulator, for the low impact docking simulator that allows people to connect to the International Space Station. So we worked with NASA and one of their contractors, and one of the things they needed was to monitor, to simulate 24 strain gauges, because they used strain gauges to ensure that the vehicle being docked is fully docked. And before they open up the air vents, or before they open the airlock, they want to make sure everything's docked perfectly, and they used strain gauge for that measurement. So Other things we see, hold on just a sec, I'm having trouble getting the slide up. I'm not sure whether my computer just locked or but I don't know if Shannon or someone else on the thing can move to the next slide.
Bob, I have you on slide 18.
Okay, and which one is slide 18?
Is that good?
Well, no. What's
resolvers?
Okay, that's fine. That's perfect. So I will muddle through with. So it should say synchros and resolvers notes. Is that where we are? Or oh, slide 18. Okay, I can see that. All right, hold on just a sec. Sorry about this, everyone.
And just cue me, Bob, and I'm happy to advance for you. Okay,
great. So, synchros and resolvers, also known as celsins. I think they stopped being called celsins in and around World War II. Back then, they were used with analog computers to control Navy gun batteries, and they were, used as rotational translators and remote controls. They're used more today as driving indicators and as sensors, but there's still, I'm sure, some out there in control. A couple of things to note is that there's really the synchro and resolver are very similar, but they're different. One's the synchro's 3-wire and a common resolver's 4-wire. So before you try and simulate a device, make sure your simulator has the correct outputs for what you're trying to drive. They can have internal or external excitation. They can have excitation frequencies, different excitation frequencies and voltages. Be careful in the accuracy and resolution. Make sure you get what you need. Output requirements are usually specified in volts RMS. Output requirements and the power output requirements are typically specified in volt amps. And then you also want to take a look at high-low accuracy and speed requirements. And consider the update rate. One of the things I just want to point out there is we get people all the time that want to sample systems at faster than their excitation frequency, and that's really very well. In a digital system, it's impossible to do, and even in an analog system, it's unrealistic. Okay, next, please. So we should be slide. Are we slide 19?
Yes, sir.
Okay. So
the notes.
So a few notes. Most devices will do input and output, and will provide or accept the excitation or reference, but do check. Most of the aerospace applications are 400 hertz, but there are. Oh, my computer just came back alive too. Hooray! But always check and make sure your system is compatible with the reference frequency you need. 28 volts is probably the most common, but there's plenty of 90 and 115 volt out there. There's a lot of old technology in the synchro resolver world. So if you're replacing a system, don't be at all surprised if it has 12-bit or sometimes even less resolution. And that may or may not be sufficient. But if you're replacing something and if you're retrofitting a SIL or a SIM, if it was 12 bits before, then 16-bit kind of modern thing is going to work without any problem. Again, there's a lot of old technology out there, and since these systems do exist for a long time, I always say, make sure the device you're considering isn't about to go end of life. Isolation may be critical. The real signals are typically coming off fully isolated coils, and so be careful using any simulated output device that's not isolated, because it can cause problems for you. And I'm back in control, so I don't have to ask you. Thank you for your help, Shannon. So at synchros resolvers, as you might expect, we have a good solution, but I won't go into it in any more depth. Another thing too that we see quite a bit of is variable differential transformers, R for rotary or L for linear. And they unlike synchros and resolvers, these are pretty much universally used as sensors. Excitation is almost always provided by the host because the RVDT or LVDT is usually just a passive device. It's a couple of coils, or I should say 3 coils typically, and a piece of iron that moves between them that causes the one coil or the other to be better coupled to the primary. Anyway, power output also all typically require less than synchro resolver. 7 volt RMS and about 0.3 VA is typically plenty. And excitation is often critical to sensor linearity. Frequencies can go from 100 hertz to 5 kilohertz, occasionally up to 10 kilohertz. Just make sure whatever device you're looking at, meets the specifications of the LVDT, RVDT you're trying to simulate. So 2, 3, and 4 wire output configurations. I think most devices probably support all 3 of those, but you should check. Like synchro resolvers, there's a lot of old technology out there. If you're rehosting a simulator or a SIL, don't be surprised if there's 12-bit or less converters in there, and that's probably sufficient. Accuracy on these devices is typically on the order of 0.1%. So 12 bits can handle that. 16 bits obviously makes it easier, but so applications for RVDTs and LVDTs, we see them all over the place in aircraft cockpits, and often HMI related, either throttle quadrants or controlling indicators. Or one of the nice things about RVDTs and LVDTs is they can be quite inexpensive, and like the synchro resolver in the application world, a lot of vendors' products that can simulate on RVDT or LVDT can also be used to measure RVDTs and LVDTs. We've got a couple of solutions, the DNA AI254 and AI256, but I won't go into those. And you can hope you're interested in those, and you can look them up on our website. So other kind of indicators are potentiometers and string pots. These are typically low accuracy, variable resistance devices. They can be simulated by a real resistor, either a programmable potentiometer or a switched real resistor board like an RTD simulator. But typically, these can be run just by a standard voltage output. A normal D to A board is usually fine to simulate a potentiometer or a string pot. Because switched resistor solutions are typically overkill. As I say, you can typically, just any analog output that does the range you need is probably going to be fine, because typical string pot and potentiometer accuracy is on the order of 1%. So I mean, even an 8-bit converter is probably okay. So pots and string notes, again, they're very, very common. We see them in cockpits, in ships and aircraft and everything, and they're often used in lighting control applications. Plus or minus 1% is typically fine. Update rates are seldom need to exceed a few hertz, and we typically recommend just use an analog output board, but you do have to be careful that you match the analog output board you select through the voltage that's going to be exciting the string pot. So, and then there's the fairly ubiquitous 0 to 20 and 4 to 20 milliamps, and they're all over the place. I'm sure everyone's familiar with them. Places you see them is output sensors, for vacuum and pressure sensors, temperature sensors, RH, and pretty much any other atmospheric sensors, and many others. It's fairly straightforward. There's not a lot to concern about because the ranges are well defined. One thing you do need to figure out is whether your device needs to sync or source current, and you can often, and it depends on the application, but often 12-bit accuracy is fine for most 20 milliamp boards, but most modern products are 16. It's seldom any requirement to ever go higher than that. Update rate is usually pretty slow. Every once in a while we run into a device that runs fast, but a kilohertz is an awfully fast 0 to 20 or 4 to 20 milliamp. it's very nice to be able to simulate open or short circuits, although you don't really need to simulate the open circuit in the 4 to 20 milliamp. I think as I read, one of the reasons they standardized on 4 to 20 milliamps rather than 0 to 20 is because they never got to 0. So if you had an open circuit, you wouldn't be getting your 4 milliamps, and you know something was wrong. So as you might expect, we have a couple of solutions for 0 to 20 and 4 to 20, one sourcing, one syncing. They're fully isolated. They simulate shorts and opens. They're 16-bit. They should work fine for you. I don't want to spend any more time on them. And then there's always the oddball interfaces. And what we've found is possibly the best way to do most of these is with either a function generator or an arbitrary waveform generator. The type of interfaces we're looking at are, variable reluctance. A function generator can sweep output voltage and frequency to show changes in rotary equipment. So if your LRU or your simulation is looking for engine speed or propeller speed or something like that, you can simulate it with a function generator. Sometimes just straight frequency out. AC analog output, because there are sensors that have an analog AC output and they need to be generated. Some motor drive signals can be simulated with a function generator, and then there's a fair number of pulse width modulated output devices, and they can be simulated either with, a lot of times with just a straight counter board, or sometimes you need to go to the fancier function generator board. Last but not least, plain vanilla, and I'm not going to spend much time on it, but and it's probably probably is the least interesting. But don't underestimate the importance of it, because I think we find that, especially in the simulator, not quite as much as in the SILs, probably half the analog outs we need are, half the signals that we need to simulate are just voltage signals, plus or minus 10 volts, or sometimes, in aircraft it can be plus or minus 28, or automotive, or truck and that kind of thing could be plus or minus 12 or 24. But there's almost always a significant requirement for voltage output. And then, as I mentioned earlier in the thing, stay tuned for part 2. I'm not sure when we'll schedule it, but hopefully we'll get it done by the end of the year, and certainly, hope to do it again with this group. Everything seems to be working fine except for my computer. So talking about avionics, and there has to be a typo somewhere in here, so it should A-Ring 429, 453. That should be 708. And 664, but the mill standard 1553, and the standard avionics buses and kind of the standard communications buses. And that's about what I have to say for today.